So
now, if you object to it and say, that can't be right, these are identical particles. It can't be if I have a bunch of, just classically, a bunch of electrons and I think all electrons are the same. And I have a representation where I name the electrons and tell you, I give you the configuration by telling you by name where they all are. And you might say, but it can't be that if you just switch 1 and 2, the whole thing will evolve differently, right? That this set of electrons, right, will do one thing, but if I switch 1 and 2, the evolution will not be what you'd expect from just switching 1 and 2. The evolution will now be entirely different. Formally, you can do it. You can find Hamiltonians that'll do that. And you might object to that. And then you say, oh, I need to symmetrize the Hamiltonian, right? There must be some symmetry constraint on the Hamiltonian. Then you might worry, where the hell did that come from? Why should the Hamiltonian have to be symmetrized? Problem won't arise if you start here. Can't write one down.
So, okay, so I think the reason for the different, I mean, I'm just not thinking, I mean, in the literature on this issue, people don't think about the particles this way, right? You just think about quantum states and the standard quantum mechanical description. That may be an error, okay? So, but are you suggesting that is it part and parcel of this picture that one's committed to the view that the ontological status of classical and quantum particles is exactly the same?
Yeah.
Yeah.
But only if they're identical particles.
Only if they're
right.
Only if they're identical
Right.
particles.
Yeah.
Not otherwise.
So that's the key. That's the key input. So I suppose implicitly, I'm sort of nervously saying that I'm just not thinking that particles in quantum mechanics are particles, and that's why I'm not thinking about it this way.
That's a fair way out.
But
it's not really. I mean, it's not really about. I mean, because they're going to say, "Well, how the hell are you thinking about them?" And then I say, "Well, I'm not really, am I? I haven't got. I haven't got an ontology."
You're acting as if you're even more thinking of them that way and insisting on from the correct.
Right. So it's a sort of
insisting on
unhappy
labeling.
marriage of like one hand refusing to think of them as particles, on the other hand sort of pretending they are like particles but weird ones.
But let me put it differently.
It would be even more natural from the point of view of quantum mechanics, I think, to use this other configuration space, since you feel even less obliged to think of the particles having intrinsic identity with labels.
Right. Yeah. Quite.
But so let me put it this way, James, maybe to make it clear. When you raised the problem, you had a permutation operator. You invoked a permutation operator.
Yeah, sure.
The permutation operator operates here.
Yeah, you were suggesting.
Okay, it transforms some mathematical object in the way you've set things up into a distinct mathematical object. Now, the claim is, if you start with this mathematics, there is no such thing as a permutation operator. It just doesn't even exist.
Yeah.
But even in your case, where you have it, you have to ask yourself, what reason do I have to believe that these two different arithmetical objects, which are clearly arithmetically different, represent distinct states?
Right.
Which means thinking a lot about this part and about what you're representing and about, now, in the case of particles, you say, in the case of particles, I know what I'm trying to represent. I'm trying to represent where they are.
So
right? That's a physical fact over here.
Yeah.
If they're really point-like particles and there's really a space, there's really a fact about where they are, and that's what that's what the content of these symbols is supposed to be getting me at, right?
Yeah. So the suggestion is that the standard way of thinking about things has surplus structure and representation. You're misled into thinking that's giving you something about information about ontology.
Yes.
Yeah. So then, I mean, I just have questions which are probably just naive. So now I want to know how you make the connection between, I mean, if this picture's right, then nothing you said is specific to fermions or bosons. But then
Absolutely.
How do I get at the fact that in the quantum formalism, in order to recover my normal theorizing, I need a distinction between fermions and bosons. I need a distinction between the ones that live in antisymmetric states and the ones that live in symmetric states, because the symmetric ones can all pile up in the same state and the antisymmetric ones can't.
Right.
So where
These
do
guys can't answer that question.
Okay.
Yeah. See, there's something interesting about this space. N2R3 or NR3, endpoints R3. It has a non-trivial topology. Not simply connected. And the universal covering space, natural thing to consider when you have a space with a non-trivial topology. You want to do the the analysis is simplified by thinking of this space with non-trivial topology as some sort of level set in the covering space. And the covering space is R32, the usual, with the points, with the identifications, coincident part points removed. Let's just say R32, the usual space. Now, it turns out that if you're thinking, at least in terms of Bohmian mechanics, let's look for Bohmian kind of dynamics. You realize that it was not essential that the wave function live on this configuration space. In the case where the configuration space is not simply connected, the more natural place for the wave function to live is on the covering space, because if you have a wave function on the covering space, a bigger space, which is consistent in the right way from fiber to fiber, from level to level, in the covering space, it'll define an unambiguous Bohmian dynamics. And it turns out that the consistency relation between going from one level to another in the covering space amounts to demanding that the wave function, so there's a fundamental group that you have when you have a non-trivial fundamental group which acts on the loops in any space. It will be non-trivial when the space is has a non-trivial topology, and the fundamental group, and it acts then on the covering space, and it acts on the fundamental group for their NR3. It's just a symmetric group on n objects, a permutation group. And the condition for consistency for a wave function defined on the covering space is to define an unambiguous dynamic. So here Q is the point of the covering space. Q1 through Qn, usual kind of description. The consistency condition, and sigma is now a permutation, an element of the fundamental group. The way things have to work out is that this has to be given by some phase factor. The relationship between, so to speak, the wave function on different levels has to be given by some phase factor. That phase factor has to be a character of the fundamental group. The fundamental group in this case, symmetric group on an object, has just two characters, a symmetric character and the anti-symmetric character, giving you naturally the possibility of fermions and bosons. So that's how fermions naturally arise from this point of view.
Right, but that's because you reintroduce the space that you originally had, but for the wave function, not for the particles.
Certainly not for the particles, and for the wave function, because the role of the wave function, how the wave function is related to the particles in this theory is to define an equation of motion for the particles through something like this. It's supposed to define a vector field defining the dynamics. What you really want is that vector field to be unambiguous. And if you reflect upon the situation, you get an unambiguous vector field for defining the dynamics, not just from a wave function on the original configuration space, but quite naturally, this is a very common kind of thing in analysis, quite naturally from a wave function on the universal covering spaces as long as it satisfies this kind of conditions, consistency condition. This is exactly the condition that it projects down unambiguously to a well-defined motion on the original space. I mean, you could have had a general wave function wouldn't do that. I mean, it would not, the motion associated with this configuration here, you would get two different motions depending upon whether you use this piece of the wave function or that piece of the wave function, as Tim was saying. You want to avoid that. It's exactly avoiding that gives you a condition like that, which forces the wave function to be anti-symmetric. But if you're interested in the possibilities for Bohm-like dynamics, you're naturally led to the possibility of fermions from this point of view. Just